Hello everyone, welcome back to another lecture on classical mechanics. And today's lecture is lecture number 11. In the last lecture or in the last few lectures, we have discussed on the Hamilton's principle. And using the Hamilton's principle, we have also derived the Euler-Lagrange equations. And that is what we have done, and then we have stopped there. In today's class, we will see the advantages of the Lagrangian formalism, and we will also see a few examples on how to apply the Euler-Lagrange equation in order to get the equations of motion of certain dynamical systems. That is our today's lecture plan. Okay, so let us go to the board and see the details. I would like to first of all explain in what way the Lagrangian formalism is somewhat advantageous. So why it is more advantageous when compared to dealing with the direct Newtonian equation. So that is the first point. So let me write down that. You have the Lagrangian formalism. So this is the first question that will come to your mind. Okay. Otherwise, you feel that we are essentially repeating the same mechanics problem, and whatever answer you already got using the Newtonian mechanics, the same kind of answer or the same answer only you are going to get in this particular case in the Lagrangian formalism also. So the question therefore arises, why the Lagrangian formalism is advantageous, or why it should be considered a better approach than the original Newton's equation. That is a question that we have. And the answer is quite simple. The first answer you already know. First answer is the Lagrangian formalism has given you the working principle behind the nature. That means working principle means the extremization principle. Nature always want to optimize certain things. That is the answer that you get. Therefore, Lagrangian formalism gives you the understanding of the mechanical systems. This is the first answer. So that is the first advantage that you know. In addition to that, do you have any further advantages? Yes, it is having an additional advantage. That's what I am going to explain. The second advantage is that if you see the equation, namely d by dt of this equation we have derived in the last class, and this is the Euler-Lagrange equation. So d by dt of the partial derivative of the Lagrangian with respect to the velocity minus the partial derivative of the Lagrangian with respect to the coordinate is equal to 0. This is the equation that you have, and this equation is valid for all q's. For all q's in the system. That is your conclusion, and this is the equation. And now you have to compare this. So let me put a bracket like this, and then let us compare this equation with this standard Newton's second law, namely F equal to ma. So now you are going to have a side-by-side comparison like this. The first equation that you have written is the one using the Hamilton's principle, namely the Lagrangian formalism. And the second expression that is written down here is the standard Newton's equation. So the question is that by looking at these two equations, can you say any advantage for the Lagrangian formalism over the other? So that is the question. And now we can see the answer by looking at this equation. It can be observed from the appearance of the equation. How it is visible is that this equation F equal to ma is a vector equation. This is a vector equation, which means that the meaning of this is this equation has to be written in scalar components like this. The x component will be equal to mass times the x component acceleration, and similarly you will have to repeat for the other two coordinates that you have. So f z equal to m times a z. So which means that the Newton's law that you are going to write down is basically a set of three scalar equations. This is your observation. And now you do the same analysis for the case of the Euler-Lagrange equation that you have written here. So I'll put a bracket here. For this one, what is your conclusion? So this is a scalar equation. There is no vector here, because you already know how we derived in the derivation. Nowhere we have said that Lagrangian will be a vector quantity, and therefore all of them will be scalar quantities. Therefore, this is a scalar equation. So the meaning is that you have to deal with, okay, this means that if you are going to use the Newton's second law, you'll have to deal with forces and acceleration, which means that they are vector quantities. And in the case of the Euler-Lagrange equation, you'll have to deal with the coordinates as scalar quantities, and the Lagrangian itself is a scalar quantity. So our conclusion is this: we will be using mathematics of vectors in the Newtonian mechanics, whereas we will be using the mathematics of scalars in the case of Lagrangian formalism. So this clearly indicates that Lagrangian formalism is having a better advantage, because doing mathematics with scalar is always comfortable when compared to performing calculations using vector quantities. You know that vector calculus is somewhat difficult when compared to scalar calculus. So in that way, you can easily understand that the Lagrangian formalism gives you an advantage. So this is the first point. The second point is this particular equation, namely the Lagrangian formalism, is the third advantage I'll write down, that this particular Lagrange equation, or I'll say that Euler-Lagrange equation, EL equation, is independent of a coordinate system. So we can say that it is coordinate free. By that, what is the meaning of saying coordinate free is that depending on a particular problem, you will have to identify what is the coordinate system that you are going to use, and then correspondingly you have to express the Euler-Lagrange equation in that particular coordinate system. But otherwise, if you are not going to refer to a particular coordinate system, the appearance of the equation will be the same in all the coordinate systems. So that is an advantage. These are the two or three advantages of the Lagrangian formalism. The primary advantage is the understanding of the Newtonian mechanics itself. That is the primary one, because that is the one that gives you the reason behind the working principle of the Newton's second law. So therefore, that takes the topmost priority of advantage. The last two examples, or last two advantages, is an additional advantage when we are working the calculation. So therefore, we are now interested to perform some calculation using this particular equation. So what is our plan, or what is the first aim of this equation is that we have this equation that you write down, d by dt of dou L by dou Q dot minus dou L by dou Q. You keep this equation one side. Okay, that is equal to 0. So now what we will do is, there is a equal to 0 here, but there is a minus here. So what I will do is, if you take this to the right hand side, we can remove the equal to 0 and put equal to here. Is it okay? So I'll put the equal to here. This is what you have. So this is the Euler-Lagrange equation. And for comparison, let us write down F equal to ma here. So what is the aim is, we'll have to perform some calculations and then understand this equation that we derived. Now, how can we do the calculation? We cannot perform any calculation using this Lagrangian formalism if you do not know the Lagrangian function. So there is a big question is there. The discussion is because the question is this: what is L? We don't have an answer, but we have a general answer. The general answer is Lagrangian is a function of Q, Q dot and T. That is the only thing we have. But this information is not enough. And in our previous discussion, we have seen that number of functions that you can write arbitrarily using mathematically, infinitely many. You yourself can write down infinitely many possible combinations of Q, Q dots and T. So that many number of combinations of functions, what are you going to do? So ultimately what you want to achieve, that should be clear to you. That is why I have written aim. Okay. So our objective is that using this equation, what is our purpose? Okay, one Gokul K want to join. So okay, admit. Okay, fine. So the objective is that first of all, we need to identify. So our question is that, first of all, we will have to identify the L, or the whatever, whether you write the script L or the normal L, that is a Lagrangian function. So that is the Lagrangian function. That is an objective. For making this objective successful, we write the Newtonian equation on the right hand side, because our purpose is very clear. We started with the Euler-Lagrange equation and Hamilton equation itself. People have discovered that principle itself to understand the Newton's law. So therefore, that is the reason why we write F equal to ma on the right side. And then you analyze dimensionally, that force will be Newtons. So let us write down the dimensions. Then this will be equal to the mass, so kilogram I can write. Then you have acceleration is meter per second square. That is okay. So Newton is identically same as this. This is okay. But similarly, if you are going to perform dimensional analysis on the left hand side, here what will you have? That is what we are planning to do. So if we are going to write down the Lagrangian here, the dimensions of the Lagrangian is written in square bracket, then d by dt. So d by dt means there will be a second. So second will be in the denominator multiplied by, there is a q dot. Q dot is going to represent the speed. Therefore, I will write down meter per second. So these things will be the dimensions in the denominator. That will be equal to the right hand side. This is a dou L. Therefore, Lagrangian dimension. I do not know the dimension. So this is the place where you have to understand. What is the meaning of the square bracket of L that you have written is, it is the physical dimensions of the Lagrangian. Now right now means, based on our previous 10 lectures, we did not get any opportunity to explain what could be the physical dimension of Lagrangian. Nor that we have got an idea for that. We didn't even get any idea of what should be the physical dimension. We didn't get any idea. What all we know is only a mathematical function. We can always write down infinitely different mathematical functions of q dots and t. And if you write down the physical dimension for all those infinite combination, each one will have a different dimension. Finally, that is what will happen. But we don't want to mess with so many expressions. We'll have to identify a suitable expression for the Lagrangian. Only then we can proceed for some calculation. That is what exactly we are doing. So the square bracket of L means the physical dimension of the Lagrangian, which we do not know. That's what is the meaning. Then divided by dou q. So q is the coordinate, and coordinate, let us say Cartesian system, we can write meter. This is what we have. So which means that, so this gives you, let us simplify, L is there, and this product will give you meter. Second and second inverse cancel. So I'll get a meter will be equal to L by M. So this looks fine. So as you can see, the dimensionally, the Lagrange equation is fine. There is no trouble. And in the case of the right hand side, you can see that Newton is there and that side is this. And you already know that both of them are equivalent. Whether you write Newton or whether you write kilogram meter per second square, they are equivalent. So this is, so there is no trouble for the dimensional analysis for the Lagrange equation, and there is no dimensional analysis trouble in the case of Newtonian mechanics. That much is clear. But what we are now interested is, we want to make an understanding between. So you see the understanding between. That is why I'm putting an arrow here like this. We need to have a correlation between, or understanding between, Euler-Lagrange equation and the Newton's law. Therefore, I'll simply copy the previous dimension analysis here. So I'll be getting kilogram meter per second square. So these two should be related. Related means the purpose of obtaining the Euler-Lagrange equation itself is to understand the Newton's law. Therefore, the Euler-Lagrange equation should now be in a position to explain the Newton's law. If it is so, that is the meaning. That is the meaning of writing this double arrow. If it is the case, the dimensionality that is there on the left hand side, which I am showing now, you follow the white color cursor. The dimensionality shown on the left hand side should be the same as the dimensionality shown on the right hand side of this line. So that means if you want to make that kind of a similarity, then we demand this particular situation. So we demand. So what are we demanding is that the dimensions of the Lagrangian divided by the meter should be the same as or either you can write equal to or this kind of symbol. That is not a problem, because this is not a numerical value. So there is nothing wrong in writing this kind of tilde symbol. So this is known as the tilde, which means it is the same as, like that you can read. So the dimensions of Lagrangian divided by dimensions of the whatever the meter that you have should be the same as that of Newton. That is the meaning. So if we demand this condition, then what will happen? Then what will happen is Euler-Lagrange equation should be in a position to explain the Newton's law. That is what is the our demand. So which means that the dimensions of the Lagrangian function should be the same as Newton multiplied by meter, because you simply do a cross multiplication, I get a Newton multiplied by meter. And basically you can understand what is Newton into meter. Newton is force, meter means distance. So this is nothing but this is force multiplied by distance, and force multiplied by distance is the work done. And work done means the dimension should be, you know what is the work done. So the work done should be in the dimensions of joules. So we say that is nothing but it is the same as energy. So our conclusion is that the dimensions of the Lagrangian should be the same as the dimensions of energy. So this is the conclusion. This is an important conclusion that we have. You should now again emphasize why you have made this conclusion is that out of the infinitely many possible ways in which you can write the Lagrangian function, q comma q dots comma t, there are infinitely many ways of writing this function. Out of those many infinite combination, you have narrowed down and identifying or choosing that Lagrangian function that has the dimensions of energy. That is the meaning. You have so many options of the Lagrangian function, but I will reject every one of them and I will only accept if the Lagrangian has the dimensions of energy. That is the meaning. And now you can ask the question, how many such possibilities can be there? Okay, infinite possibilities are there, you are rejecting. Finally, we will be coming down to a certain finite number of possibilities where they all will have the dimensions of energy. Can you identify them? The answer is that you cannot straight away identify what could be the Lagrangian. So this is where the difficulty is. We cannot write down any function of the Lagrangian and then it will represent the Newtonian equation. And therefore what will happen is, even though this is the first important clue that you got, we will have to now construct. So this clearly tells me that we will have to construct the Lagrangian, okay, so as to have so the conclusion also I am writing, because writing the equation and putting a box, that's fine. But what is that we are understanding from that is that we will have to construct a Lagrangian function in such a way that the dimension will be the same as the energy, which means that anything which is of the form of square of that or square root of that, all such possibilities will vanish. That is what it means to say. So now we don't have, but however, remember, this is the final, another important point is that even though this conclusion is right now available to us, we still don't have a proper way of obtaining the Lagrangian function. You cannot say that this could be the Lagrangian function. Okay. So this gives you that this opens up that there are many possibilities. We cannot say infinitely many, but still we can say that there are many possibilities. What is the meaning of many possibilities is that I will write down many possible functions are possible. Many possible functions can be there. So the conclusion should be clear. Only then we will be able to understand or justify when we write the next step. Okay. So out of the infinitely many possibilities, you narrow down using this dimensional analysis. And even after narrowing down, you cannot say that there exists only one function. That cannot be made. That is the important statement, which means that even now you are having a different, or at least there are many possible functions are uh, can be written down so as to satisfy this condition. Okay, so this means, making a final conclusion, this means the Lagrangian function is not unique for a given dynamical system. So the last conclusion that you have written, this is the important one. Finally, after the discussion, this is the conclusion. Once we identify, or once we give you a physical system to you, can you say that this is the only Lagrangian possible? The answer is no. The given Lagrangian can be one Lagrangian, that is fine. But in addition to that, there can be additional Lagrangians which will still work correctly for the given physical system. That is the meaning. Not unique means in addition to one of the Lagrangians, another Lagrangian may also work. That is the meaning. So this conclusion is very important, and the Lagrangian is not a unique function. Okay, you can discover one of the best working Lagrangian, that's fine, but there is no way you can say that this is the only thing. So this is the very crucially important conclusion. So what happened therefore is, okay, keeping this particular conclusion, we still don't have a function with you. Okay, even now you don't have a function. Only if you have a Lagrangian function, we can do some calculation. Therefore, what people have done is, people have done the reverse calculation. So reverse calculation means it is like this. If I say that integral of something, I'll say like this: integral of something is there here. So the answer should be equal to something like x to the power of 3 by 10. Integral of something is this x to the power of 3 by 10, which means that this is the answer. Some integration gives you this kind of an answer, x cube by 10. Can you find out what is that something? That is a question. No, it's a kind of reverse question. So what you do is you work in a reverse way and then find out if x to the power of 3 by 10 should be my answer, what should be the function to be there in the integration in here. So what should be here? Like that you can perform some reverse calculation. So people have done this kind of a reverse calculation. What kind of reverse calculation is this? If, let me write down here, if the equation of motion, EOM means equation of motion. If equation of motion is to be obtained, if equation of motion is to be obtained using Lagrange equations, I'll say EL equation means Euler-Lagrange equations. If equation of motion is to be obtained using the Euler-Lagrange equations, then what should be, or what is a possible Lagrangian function? So this is the question which is equivalent to what I am asking here. Okay, one more candidate want to join. Harsha, okay, admit. Is it okay? So is this question should be very similar to this particular question that you have. So here you have integral of something. Maybe this one I have, let me write down this. The integral of something should be equal to given answer. So answer is given to you. If integral of something must be equal to the given answer, then find that something. You can easily understand this particular problem. Now, once you understand this, come here and read. I want to obtain the equation of motion as the final answer. That is an answer. How do you know that answer? Means it is already obtained using Newton's second law. So like that you keep the answer. So answer is there already with me. Equation of motion is already obtained using the Newton's law and I know the answer. If it is so, what Lagrangian should I use now? And then substitute in the Euler-Lagrange equation so that I'll get the same answer. So this question and this question you'll have to compare and then understand what exactly we are doing. This is a kind of reverse calculation that keeping the answer with you, you go backward and ask what could be a possible Lagrangian function that you can substitute in the Euler-Lagrange equation. That is what people have done. And after doing this analysis, people found out that one possible, so the important word is possible. possible is different, only is different. It is not a only Lagrangian function. That is important. It is a possible Lagrangian function. Okay, which means that in addition to this Lagrangian function, some other function can also work very nicely. That is the meaning. Okay, so now after people have done this particular analysis, what is the conclusion people have got is that a possible Lagrangian function could be equal to the kinetic energy minus the potential energy. And you see that each one of the terms is having the dimensions of energy, and certainly you can always ask why not T plus V. One more student is joining. Okay, admit. Fine. Okay, so after doing the reverse calculation, you know what is the understanding of reverse calculation, you understood, right? Using the reverse calculation, people identified that one possible Lagrangian that works nicely with the Euler-Lagrange equation is given by the kinetic energy minus the potential energy. You can always ask the question, why not? So the question is this, why not T plus V? You can easily give the answer. Now you don't require answer. You yourself know the answer. Why not T plus V means if you consider the Lagrangian to be equal to T plus V, then you won't get the equation of motion. Equation of motion is the Newton's second law. That's what you have to remember. You won't get the Newton's second law. Therefore, this particular function L equal to T plus V doesn't work. So it happens to be one of the infinite combinations. There are infinitely many combinations are there for Lagrangian. This happens to be one among them that doesn't fit into our dimensional analysis. It doesn't fit. Even though it has a dimensionality wise, it is fine. But this particular selection of the Lagrangian doesn't fit to generate the equation of motion. So that is why the aim that I have written should be very clear. Our aim is that we want to generate. So you go back and read this. That's what we have written. The aim of the analysis that we are going to do is you discover the suitable Lagrangian in order that the Euler-Lagrange equation will generate the Newton's law. You say that this will generate the Newton's second law. In such a way, you discover the Lagrangian. That is what I have already written here. You see, I have already written here what is Lagrangian. Okay, so now we are making that conclusion and then coming to this particular place that people have identified that by doing the reverse calculation, people identified that L equal to T minus V is a good option. So let me therefore write down the conclusion now. So this means in addition to T minus V, there can be so I'm writing this conclusion for clarity. This means, what is the meaning is, this means in addition to L equal to T minus V, there can be other functions which are capable of reproducing the equation of motion okay, that's it, that is enough. So starting from Euler-Lagrange equation, that is understood. So I'll put full stop here. So this particular conclusion that we have done is the important conclusion. Okay, so at least now the aim is clear what we are doing. The reverse calculation is quite simple. So we have to take some of the simple examples and perform reverse calculation. It is as simple as any other problem that you have. If you have a mathematics problem, generally what will you do? In an exercise problem, generally if you are not getting the answer, what will you do? You turn your book and see the last page where answer is there. Now once you see the answer, you try to do something and get the answer right. That is the trick that you are doing. So once the answer is known to you, you try to generate that. That is exactly the reverse work that people have done. And that is the one which gave you the expression T minus V. So that is where we have to remember. And it doesn't mean that T minus V is always the only option. That is also very important. In addition to the T minus V expression, there can be, that's what I'm reading here, there can be other functions which are capable of reproducing the equation of motion. But then the immediate question comes to, then why don't you write down all those expressions, but which we do not know. So that is the point. That is easily understood, or if you want, you can write down, which we do not know. So mathematics gives you a lot of possibilities. Okay, you cannot always generate all possible solution. That is not always possible. So this is where you can see the power of mathematics. Okay, the mathematics always puts you puzzle, and then finding all possible solutions is not easy job. At least we are happy that we were able to identify one function Lagrangian which works very nicely. That is what is the conclusion. Okay, mathematics accepts even more functions, but we are unable to discover such kinds of functions. So this is the very important conclusion. Now once you have this conclusion, and once you have the expression T, the only thing is you should know is the T that is written here is actually the kinetic energy, and then the V will be a potential energy. So only that much you remember. So once you know this, the expression is given by the Lagrangian is this, we can take an example problem and then solve it. So that's what we will do now. So let me go to the next side of the board, and then we'll take an example. But before we take an example, how to write kinetic energy, we'll see. First, let us see how to write kinetic energy. Then we can take an example. So here I'll write down. So the kinetic energy, the first part, in order to solve the problem, we need the kinetic energy. So this is generally written as half mv square. This is how we generally write down. But in this expression, what you understand is half m, velocity is a vector quantity. So you have to remember like this, velocity is a vector quantity. Then this is a square is there. That is the meaning of this. And now this is not always half mv square. We can't use like this because we are now going to use, in the case of the Lagrangian mechanics, everything should be a function of q dot, and then a time. So the Lagrangian should be a function of this. You don't have velocity here. You see, q is the coordinate, generalized coordinate, and the q dot represent the speed. Okay, and then you have the t, but you don't have directly something like a v square. Okay, so therefore what you do is you make a small a change in this one, and then rewrite this particular expression in possible coordinate systems. So what you'll have to understand is that if you are going to discuss in different coordinate systems, this has to be expressed differently. So half m into, what you understand by modulus of v square is that we can write down that this is x dot square plus y dot square. What is the meaning of x dot y dot, that you know? That's why I'm directly writing. X dot is the velocity in x direction, velocity in y direction in 2D. So this is the situation for 2D, and in the case of the 3D you can write down like this. And it is very clear that this is a Cartesian system. So we every time we should not write half mv square. Okay, we instead of half mv square, we should always write x dot square, y dot square, z dot square if it is Cartesian. Otherwise you'll have to convert it into appropriate polar coordinate. The reason why we are doing this is because of the q dot here. So you should always have a dotted version of the variable rather than v. We can't use v in this particular equation. Everything should be dotted version, means time derivative of something. Like that only everything should come. Only when you write expressions like that, you will be able to perform the derivatives that are appearing in the Euler-Lagrange equation. That is the reason. You have the, let me explain. So what is the meaning of this is, you have an expression, right? A partial derivative of dou q dot. What is the meaning? The meaning is, if you are going to consider the Cartesian system, then this is dou x dot. So the meaning of this particular expression is, perform the partial derivative of the Lagrangian with respect to the x dot. So with respect to the x dot means, in this expression x dot is not there. So do the derivative means, what will you do? You will think that it is 0 because x dot is not there, you will put 0, right? That kind of mistake should not come. So that is why everything should be expressed in terms of x dot, y dot, z dot. And in case if you are going to do in polar system, then the respective variable has to come. That is the meaning that I am trying to explain. Now let us consider a 2D situation, and then suppose we convert, or suppose that we are working in a two-dimensional polar coordinate system, then what will happen? So this is the simplest thing that we can do, and once you understand this, the rest of the calculations are easily you can follow. So in the case of the 2D polar system, let me write down that this is a polar system. We need to obtain what is the meaning of x dot square plus y dot square, because anyway this half m, this is not important, let's forget about this. So let me put this half m into this, that is okay. But what is now required is x dot square plus y dot square is what we will have to convert to. So this is the one which we will have to convert to 2D polar. So for that what you do is quite simple, but only for 2D polar we will do the steps. The remaining 3D polar we will write down quickly, because only one more term you will have to add. We need not do all the derivations. Okay. So let me therefore explain this. X equal to r cos theta you have. And therefore what will happen is, you can get an x dot here. X dot will be equal to r into minus sin theta into theta dot, then plus cos theta into r dot. And once you have this, you also have a similar expression. So let me write down here, y equal to r sin theta. So x equal to r cos theta and y equal to r sin theta are the equations in 2D. That is why I am writing like this. Then you have y dot, take a time derivative. Hello? Hello, are you able to hear?
Yes, sir. Yes, sir.
Okay, I am getting error message. Internet connection is lost. Is it? Shall I proceed now? No, I am getting error message saying that internet connection is lost.
So now it's not presenting, but we can hear you.
That what have that green color board has disappeared?
Yes, sir.
Okay.
Yes, sir,
Okay, again I will do it. Okay, now it says okay. Okay, is the board now visible?
Yes, sir.
Okay. Sir, okay. So we'll be having the y dot. So we'll take the time derivative. We'll get r into cos theta into theta dot plus sin theta into r dot. So once you have this, we can now square and add them. So let us therefore write down x dot square plus y dot square will be equal to, let us square this expression. We will be getting r square theta dot square, then you have a sin square theta, then plus this will be equal to r dot square cos square theta minus or we'll write down plus 2 into minus r theta dot sine theta is it correct? You check. Minus r theta dot sine theta, yeah, into r dot into cos theta. Okay, these are the terms there. Then plus, for the second part, let us write down that this is plus r square r square. So here I am writing this one, r square theta dot square cos square theta plus r dot square sine square theta, then plus 2 times r cos theta theta dot sine theta r dot. That's all. So these are all the terms for the second one. So I'll put a square bracket. So the first square bracket corresponds to the x dot square. Second square bracket corresponds to y dot square. And the simplification is somewhat easy because you will be getting terms like sine square theta and cos square theta. Okay, so they will become 1. So that is why it is advantage. And in addition, you see the last term, I mean that 1, 2, 3. The third term in the square bracket, okay, third term in this square bracket cancels. So because of these reasons, the simplification is somewhat easy and we will get a simple result like this. Our conclusion is that if we simplify, we will be getting r square. Now let me write down here r dot square plus r square theta dot square. That's all. So you got a simple result like this. Okay, so this is valid in the case of two-dimensional polar system. So for 2D polar, fine, this looks fine. And if you are going to do, or if you are going to move for three-dimensional case, you have two options. One option is that you do for cylindrical polar. The other one is for three-dimensional spherical polar. So two options are there. Therefore, the expression may go a little bit lengthier, but not difficult. So we will not do that lengthy expression. Okay, instead of having this kind of an expression which have 1, 2, 3, 4, 5, 6 terms are there. There you may get 9 terms and 12 terms if you are going. That's all about it. But ultimately what happens is there are many terms will come in a very similar style where sine square theta, cos square theta will always come. So they will add up and become 1. Some of the terms will get cancelled. So ultimately, even for the case of the 3D systems, you will be getting simple result. So that is the conclusion. So let me therefore write down what happens in the case of the 3D system. So I'll write down this. This will become a very small change will be there. R square, I mean r dot square plus r square theta dot square plus z dot square. So this is the only change will come. Therefore, this is also fairly simple in the case of the 3D, but now this is cylindrical system. The expression is same. I can write down that this is actually velocity v square. Basically, this is v square. So I'll write down that v square is the velocity square, which we are writing it as x dot square plus y dot square plus z dot square. Or I will not write this. There is a gap here. I'll write here. So v square will be equal to this. So this is one important conclusion. Another conclusion is that we will have to move to the, what happened, this is going. Okay. So in the case of the three-dimensional spherical system also, the expression is somewhat simple. So that also I will write down v square equal to same r dot square. So the advantage is that the first two expressions are same. So therefore you can easy to remember r square theta dot square plus the third term changes to r square sine square theta into phi dot square. So this is the change. You know that additional variable phi comes into picture for the case of spherical, and that's why you have that. And you also know what is the reason for the r sin theta factor. Wherever you go to the spherical polar coordinate system, you always encounter a term r sin theta, and you know what it is. R sin theta is basically, r is the radius of the sphere, and r sin theta is the shadow of that radius. If the sunlight is falling from the top, and if you have the radius vector, then what is the shadow that is falling on the ground horizontal surface? That is r sin theta. That is why r sin theta will come many times in this particular expression, and this r sin theta explanation, if you have done the derivation, you will feel more comfortable. So let me also put this conclusion. You will have to repeatedly use this expression. That is why I am making a box here. So depending on the coordinate system, you directly write down. You please don't derive. In the examination, you don't have to derive the expression for v square. That is not required. Okay, once you understand this, you keep these expressions and then use it directly in solving the problems. So this is the expression for the three-dimensional spherical system. That's all. So these are the main expression for the velocity, and remember this is also velocity square. So the first one I have written only x square plus y square. So that is nothing but it is also same as velocity square in the case of two-dimensional. So all of them are v square. Then you simply multiply this by 1 by 2 into m. Then you get the kinetic energy. So why we are making this explanation is, in the case of the Lagrangian, you have a t minus v, and this is exactly t. So for t, we will be using this expression of mv square, where this v square is the one you will have to replace this v square by the expressions in the boxes. So this is the main result that we will be using. And only information I will tell regarding the spherical polar coordinate system. You can always do this. It's not a difficult one. Maybe it will take 5 to 10 steps. That's all. Within 5 to 10 steps, you can simplify this. It's not a difficult. I'll only tell how to start the spherical polar system. So you'll be doing like this. You'll have to write down first of all the expressions for the x, y, z in the case of 3D spherical system. Now how do you write? Now writing is also easy. Let me explain. See, memorizing is different, but if you understand something and write, it will be much more easy. So what you do is, you first start with what is known right from the school. X equal to r cos theta and y equal to r sin theta is the one which is quite familiar to you. Therefore, you write that first. So how did you write? You write in this direction. That means first I write this equation, and the second one I write this equation. So the direction is like this. Now what you do is, for the case of the three-dimensional spherical system, to make things easy to remember, you write in this direction. That means you start writing from the bottom and then go like this. But the first equation to be written is the one corresponding to the r cos theta, isn't it? So therefore we write r cos theta here. So that means the first term will be the one corresponding to the cos theta term. So here also first I write. So this is the starting point. You start like this and then move like that. After that, what is there? The second one is r sin theta. So you write r sin theta. And here also r sin theta, because there is nothing extra here. So repeat that 2 times. So this is over. Then after that, what you do is, in the case of the 3D system, you have r comma theta comma phi. You have 3 variables are there. So now you have to bring the phi component. So for that, what you do is, you bring the phi component now. Okay, but when you are bringing the phi component, remember once again that the first term that you write is always cos theta. The second term that we will be writing will be the sin theta. So therefore, I will write the first term will be always the cos term. The second term will be the sin term. Okay, so now I finished this. Now I am writing like this. This cos phi and sin phi. So if you write like this, there is nothing that you try to remember. If you try to remember, you also try to forget, right? Most of them, that's what happens. Therefore, rather than simply closing your eye, or if you look at the sky and read x equal to r sin theta cos phi, then you'll always make a mistake. Most probably mistake will be the interchanging phi and theta. Okay, that is a place where mistakes can come. So if the starting point itself goes wrong, then all the steps will go wrong. So that is why I am telling like this. So you start writing down this. Now once this is over, and that after that it is quite simple. Calculate x dot, calculate y dot, and then square and add. That's all. Then you will be getting this expression. So our conclusion is now clear in this particular class, that we have seen what is the advantages, some of the advantages of having the Lagrangian formalism. This is not the only advantage. You still have more advantages, which of course I have not explained right now. For the time being, this is fine. If you ask still more advantages are there, you have still more advantages in terms of mathematics. You see the phase space variables are there, and any property that you are going to obtain because of this calculation will be the direct consequence of the geometric properties of the phase space. So that is, of course, that's a mathematical advantage. So physically we are not much interested, but still that is also considered as an advantage. So what is an advantage in addition to the Lagrangian formalism that we have seen? First 3 points is that any property that is going to emerge out of these calculations mathematically will be the direct consequence of the geometrical properties of the phase space. And phase space itself is higher dimensional mathematical space. So instead of saying geometrical properties, we say that they are topological properties. Okay. And then in the phase space, you have the curve or you have the trajectory. And since it is not three-dimensional, we better rename the trajectory to a manifold. Therefore, what happens is that if you are going to say that I am going to study the geometrical properties of the trajectories, you convert this English statement to a higher dimensional situation, then it becomes topological properties of the manifolds. So this is a conclusion from the pure mathematical point of view. So there are many mathematicians who work on topology, differential geometry. So they will be studying more and more properties of the phase space. Phase space itself is a mathematical space. So those mathematical properties will be directly reflected onto the physical system, and that reflection is what you are going to see. What are you going to see means pendulum is oscillating. That's what you are going to see. So what you are going to see is a reflection of the mathematical properties. Mathematical properties are not directly visible to you. So that will be known only when you work out the corresponding mathematics, namely the differential geometry and topology. So you can see how things are working. Okay, physics is working based on the rules of the mathematics. So mathematics will dictate you do this, and physics will simply do it. It won't ask the question, why should I obey? Physics will not ask why I should obey mathematics. Okay, mathematics will put the rule. This is what you have to do. And physics means, by the way, remember, physics means every other thing. Okay, whether it's a biological system, all branches of engineering, everything comes under one head. The entire thing of the universe will obey what mathematics dictates. And that is why I say that the mathematics has that power. Okay, so learning mathematics will always give you more and more ability to understand nature. Okay, and among the nature, physics happens to be one of the examples of nature. So our today's conclusion is so clear. Primary objective is to understand what is the advantage of the Lagrangian formalism, followed by how do you identify the Lagrangian. Lagrangian is not a unique function. That's very important. One possible function could be t minus v. That's all about it. And if it is so, how to write down the expression for the kinetic energy in different coordinate systems. These are the three of them, most probably. There are other coordinate systems are there, like hyperbolic coordinate system, parabolic system, etc., which are not required. If it is some special situation is there, at that time we can apply. But right now, three of them only coordinate system we will be using. So this is the plan. And once we have this, how to now take an example problem and then solve it. So that we will see in the next class.